In this video, we're going to examine what the maximum power transfer theorem says about reflection coefficients of S networks. Let's start with the standard picture of an S-parameter network, but note that I've added an unusual reflection coefficient on the left called gamma dp. This is the implied reflection coefficient of the driving point on the left of the transmission line. We usually think about the driving point impedance ZdP, but Z and gamma map to each other one for one, so we can define a gamma dp if we feel like it. We're curious about what gamma dp will be if we're trying to achieve maximum power transfer. Great, to get maximum power transfer, we need ZdP to be a conjugate match to ZS, so let's assume that. And that has the implication that the resistance of S is equal to the resistance of the driving point, so Rs is RdP, and that the reactance XS is the opposite of XdP, so there's a minus sign here. We can define gamma dp using the reflection coefficient formula. And we're going to want to compare it to gamma s in a moment. So I took the step of rationalizing the denominator, sort of multiplied the top and bottom by this term. And then I distributed the complex and the real terms over here. So this is real, because the j's multiplying cancel each other out. This is complex. We can do the same thing with gamma s. And if we look closely, we can see something interesting about these expressions. The first two terms in the denominator are going to be purely real and identical. Here rdp is equal to rs, xdp squared is equal to xs squared. But this third term has x in and xs in it, and those two have opposite signs. So that means the driving point impedance is the complex conjugate of the source impedance under max power transfer conditions. And if the transmission line weren't there, that'd also be true. Gamma in would be gamma s star. Because there's a transmission line, gamma in is related to gamma s star, additionally by the phase that you pick up on the transmission line. But I think that's cool. Conjugate impedance match implies a conjugate reflection coefficient match. This also brings out one kind of weird detail about the maximum power transfer theorem. Gamma in is only 0 if gamma s is also 0. So when we're trying to maximize power transfer, we're going to have reflections on the line. And that's weird. We just had a video set where we thought about power coming in and some of it being transferred into the load and the rest being reflected. And that's a great picture for real loads, and in particular for matched real loads. But when your source is mismatched, you have kind of a weirder equation. And in particular, if your source is complex, you can think of this wave reflection as providing a phase shift at the input, which helps cancel out the complex part of the source. So there are reasons reflections might exist, and those are particularly easy to justify for complex sources in load, where you need a phase shift in your wave to cancel out the imaginary part. So this detail about reflection suggests some interesting design choices you have when you build matching networks, especially if both the source and the load are mismatched. One kind of design philosophy is that you can build a reflectionless line. And that requires two matching networks, one that matches the source, one that matches the load, and both of them match to the line impedance of Z0. And so waves on this line will terminate on the source or terminate on the load. It's also possible to instead ditch the second matching network and just match the first matching network to the driving point impedance here. This is a more complicated match to design. It's called a biconjugate match. And the bandwidth of it might be kind of narrow because ZdP changes with frequency, since the transmission line will rotate your phase by different amounts at different frequencies. But maybe this is the right decision for you. In particular, if your matching networks are kind of high loss, maybe you don't need to, maybe you can't pay the power that you would lose going through two. This hints at the richness of RF design choices, and this is really just scratching the surface, because there are many ways to implement both of these matching networks that allow you to build kind of robust, wideband, low loss radio frequency systems. So, in summary, a conjugate match between the driving point and the source implies that the reflection coefficient is the conjugate of the source, and that gamma in on your S parameter network is related to the source conjugate just by the phase of the transmission line. Maximum power transfer also doesn't imply that you have zero reflections. And you have design choices when you build RF systems and matching networks. You can design reflectionless systems or conjugate match systems.